Hello, my name is Neil Giridharan, and I'm a first-year PhD student at UC Berkeley, advised by Natasha Crooks, and today I'll be talking to you about Wendy, a new leader-based Byzantine fault-tolerant consensus protocol. So Byzantine fault-tolerant consensus protocols are a major performance bottleneck for blockchains. They suffer from high latency, low throughput, and limited scalability. And this is primarily the result of high communication costs, both the communication complexity and the number of rounds of communication, as well as the use of expensive cryptography. Our goal with Wendy was to achieve three major properties: linearity, optimistic responsiveness, and optimal latency. Linearity is in terms of communication complexity, in terms of the number of authenticators that are sent out in the protocol. Optimistic responsiveness refers to the fact that the commit latency depends only on the actual network delays and not on an upper bound, known as delta. And optimal latency is that we should achieve no worse than 2 rounds of communication. So prior work compromised on one of these dimensions. PBFT compromised on communication complexity since a cubic number of authenticators were sent out during the view change procedure. Hot stuff compromised on latency in that it has 3 rounds to commit instead of 2 in PBFT and Tendermint. And Tendermint compromised on optimistic responsiveness since its commit latency depends on delta. Wendy achieves all these properties. Achieves linear communication complexity, optimistic responsiveness, and optimal latency in that it has a 1-round fast path and 2 rounds in the worst case to commit. Our core insight to achieve this is the use of an aggregate signature scheme with constant pairing verification costs. And we're able to design the scheme to have these properties as we're able to take advantage of the fact that these replicas are synchronized to be in the same view. And the leader sort of uses the aggregate signature scheme to come up with the proof of no commit, which sort of is able to succinctly prove to the replicas that certain values in the view change could not have been committed. And this is what is able to get over sort of the liveness problems you get when you try to sort of achieve these properties naively. So we implemented Wendy and compared it with hot stuff. And sort of the green line shows Wendy where the fast path is always taken. The orange line shows the 2-round worst case of Wendy, and the blue line shows hot stuff. And as you can see, both the fast path Wendy and the 2-round Wendy achieve better latency than hot stuff. Now the throughput is worse, and this is sort of a result of the fact that all these protocols are pipelined. And so with the pipeline protocols, the throughput is a function of the batch size divided by the actual round latency. And since with fast Wendy, we have to sort of wait for more replicas to respond than in Wendy, then the throughput is slightly lower.